We're now going to look at a few examples of the statistical properties bias, linearity, reproducibility, and repeatability that are used in the evaluation of the reliability of a measurement system. The learning objectives are to be able to calculate the bias in a gauge on our study. We also want to be able to explain what repeatability and reproducibility mean and how these both affect precision. And then given an estimate for the variation from the equipment, we're calling that here sigma E, where E is for equipment, and an estimation for the variation due to the operators, which we're calling sigma O, where O is for operator. We want to be able to calculate the total variability from the measurement system, which is the gauge error, or sigma G. We also want to understand as a rule of thumb that the overall equipment error should be small compared to the process variation, and check then that the overall error, sigma G, is small too compared to the overall process variation, sigma P, or less than 10%. We also have a short example for linearity, but that's not just for your interest in this case. Okay, again, we go through our chart again. We have a measurement value due to a true value and then to variation. This variation is due to true variation, so long and short-term process variation and measurement variation. And again, we can have sampling variation, measurement validity problems, and measurement reliability. So what we use to evaluate then, that is the measurement bias, which we want this to be near 0. And this means that our resolution should be good, and we should have variability which is much smaller than the variability in the product it's used to measure. We need to have stability with time. Our bias doesn't change with time, and our bias doesn't change with the range of values that we're measuring, no linearity problem. Measurement precision should be high. Variability due to the equipment, which we call repeatability, and variability due to operators, which we call reducibility, should be small. Again, we had the definitions from last time: bias, precision, linearity, stability, and resolution. We looked at examples with large bias when even though the same piece of equipment is measuring the same part, there's a distribution of the readings. And the average of those readings, how it differs from the true value, is called the bias. And so you can have a large bias or a small bias. And so to calculate that, we have an example. Here we have 10 readings of a 1-inch gauge, of a 1-inch block by a caliper. And we're interested in the bias of the caliper in this range. So what we want to do is to sum up all of these values and calculate again, these values are distributed. They're not all exactly the same, even though they should be exactly the same. They're distributed around a mean value. So the mean value, we're going to estimate this with an X bar value. So we add these all up, we get 10.0357. X bar is 10.0357 this is wrong. Radia, let's erase this just a second. The 10.357 inches. So X bar is 10.357 divided by 10, or 1.0357. So our average value here for these 10 measurements is 1.0357. So bias is the difference between this measured value, this measured average, and the real value, the true standard value. So we get there, the bias is 0.0357 inch. And this means that the caliper gives on average values that are larger than the true value by 0.0357. So you should be able to calculate bias given a set of measurement values and on a standard. Now, we also looked at linearity and stability. linearity. So you have a bias value here, and we have a range of values. For example, low temperature to high temperature, short to long, thick to thin, or thin to thick. If the bias doesn't change, then you have no linearity problem. But if it changes, better or worse, either way, there's a linearity problem. We also looked at stability, which is to do with time. If your variation changes, stays stable over time, or if it changes and becomes unstable over time. We want to have an example now of linearity. This is an example taken from the textbook. It's a case study comparing speedometers. So the old speedometer for a car is under evaluation. And the new speedometer, which we assume here is our reference value, it's accurately measuring the speed. This is our reference reading. This is our new speedometer. They're not the same. There's a bias. There's a difference between these two pieces of equipment. And so what we see here is that we have a range of values from 5 miles per hour to what, about 75 miles per hour? And what we see is the bias is the difference between the old speedometer and our reference, the new speedometer. And you can see that this difference is changing as we go from low values to high values. Now, if we didn't have a linearity problem, we could have a constant bias. So it means that they're not reading the same speed, but we always have the same difference. So this would show no linearity problem, a stable, no linearity problem. It's stable over the entire range of values. But here we see the bias increases at higher speeds. So we definitely have this is an example of a linearity problem. And as we don't have an example here, but if the variation would change with time, we would have a stability problem. And so what could be interesting then for us, even in this context of this short introduction, is what could cause a linearity problem? What could cause an instability problem or a stability problem? So for linearity, as your range of values change, you end up getting a different bias. This could be operator skill. As your skill of your operator changes, you end up with a different bias, an increased bias. As the operator gets tired, your bias increases. As the part sizes, maybe the part sizes are different. You could have, as your part sizes get bigger, you end up having more of a bias. The accuracy of the measurements differs from the true value more. You could have some problem with maintenance. So maybe the filters are getting clogged, or you have corrosion, or rust, or dust, or some kind of cleanliness factor. You could have possibly some kind of distortion of the equipment itself as the part size changes. And an important one to remember is the environment. You may have temperature effect, you may have humidity effect, vibration, et cetera, et cetera. And so as we said before, you need to check, especially the environment, to see if maybe you have some underlying factor that could be affecting your linearity or stability. And causes of instability, when the variation gets larger, is often caused by aging of the equipment. Or yes, also environmental drifts are important. As the humidity increases with time, or the temperature increases with time, you end up getting more or less precision, more variability in your measurements, and showing an instability problem. So again, this is an example, but something definitely to think about for an MSA. Now we want to look a little more closely at evaluating precision. We said instrument variability can come from two sources, repeatability and reproducibility. Repeatability error comes from the instrument hardware. that prevents the instrument from giving identical readings when measuring the same unit of a product repeatedly using the same operator. So we emphasize here, same unit, same operator, and it's the same instrument, of course. On this, everything's the same, but you get a variety of readings. Reproducibility errors arise from, now this time, different operators using the same instrument on the same part. Just putting that in for emphasis. Operators can use the instrument, maybe not intentionally, but slightly differently, preventing the instrument from giving identical readings when measuring the same unit with different operators. So repeatability error and reproducibility error are going to be quantified by standard deviations of readings. Repeatability by the standard deviation from readings taken repeatedly on the same unit by the same operator. Reproducibility, did I say that right? Repeatability is the error is estimated by the standard deviation of readings from the instrument taken repeatedly on the same unit by the same operator, whereas reproducibility, that error is estimated by or quantified by the standard deviation of the readings taken by different operators on the same unit. And so here we have some pictures. Here we have operator A taking same unit, same measurements, same equipment, and he's all over the place. He gets a distribution of values, maybe all around some kind of center mean, but they're never the same. So he's got this mean value, and we can estimate his repeatability error, which we're calling sigma e, as the variation of these measurements, as opposed to reproducibility, where here we have three different operators all taking measurements. And again, all of those, yes, they're not exactly the same, but we're looking here, we're interested in the difference between the well, maybe I better not write that in. We're interested in the difference between the operators in this case. We're interested in the variability on the same part with the same equipment, but tested by a different operator. And say they run again, they don't run on operator A, B, and C, actually similar results. Operator A has drifted towards the center there. So you can see that in this example, we have variability due to the individual operators. Now we want to look at an example. Again, we don't want to go through all the calculations, but just to give you an idea. So in this case, we're using a caliper to measure the diameter, dial caliper to measure the diameter of rods of metal. So what we need to do is to make sure there's a set and documented, so we write things that seem obvious. You want to document your procedures that's going to be followed exactly by all operators. And these operators, we mentioned it before, are often called appraisers. They're doing the appraisal. So let's select M operators. We're going to test N parts, and we're going to do, each operator will do R trials. This gives you an idea of how much data we're going to collect. And it's important, you want to use appraisers who normally perform the measurement, who are familiar with the equipment and the procedures. So you want to select sample parts too that represent the entire spread of the process. Because if you don't do this, in the end, we talked about this, you're going to be comparing the error due to the equipment to the error, the entire process spread, the error due to the process. And so you want to make sure that the sample parts are representative of the entire process. Otherwise, you may end up overstating your measurement error. And we'll see that a little bit later. You want to randomize your measurements, make sure there's no other factor. So each part by each operator for the R trials should be randomized. And of course, if you have larger number of parts and more readings or more operators, more appraisers, you get results that are going to, you'll have a higher confidence in these results that you get. But these numbers have to be balanced with the time, the cost, and the disruption of your production system. We then want to compute key statistics to evaluate the repeatability and the reproducibility. And then you evaluate these against acceptance criteria. So we'll look at that as well. So let's go through then in this example. And first thing, if we have 3 operators and 15 parts, and each operator measures each part 3 times, we're going to end up with 135 data points. So already with this small example, we're going to have 135 data points. And here they are. We have 3 operators, and we have 15 parts, and each operator runs 3 trials. Now, again, we're not going to evaluate all the data, but we can calculate the sample standard deviation. For example, here is the sample standard deviation for operator A, part number 1, and these 3 trials, and various other statistics. We can also calculate the overall sample standard deviation for that operator for all different parts that they've measured. And so the 3 things we want to point out here are, number 1, from 134 data points, we can calculate here an overall, so an estimate for the overall error, the variability of all the data that we have here. We can also, and we're not doing it here, this is in the book, but we're not doing it here. We can also calculate the repeatability error. Just erase this here. Again, the estimate from the sample standard deviations on the same unit from one operator. So for example, for unit number 1, operator C, we can go ahead and estimate then the sample standard deviation for that one part by that one operator. And if we combine all of those, which again, we're not doing in this course, but it's easy enough to do, it just takes a statistical package normally to help you, we can calculate an overall estimation for the equipment error, the repeatability error. And E, again, E is for equipment. And here in this example, it's 0.0014 inches. Next, we have the reproducibility error. And so for the reproducibility error, I'll erase this here. There. It's the estimate of the sample standard deviation on the same unit for all 3 operators. It's a little hard for me to show since I've got the boxes in the way, but if you have one unit and you have operator A, operator B, and operator C, I've kind of hidden it here, but you have variations for each of those. And we can compile those to get an estimate of the overall variation for the operator error, so sigma sub O, and in this case it's 0.0028 inches. So we use the data that we have, we calculate these statistics using our data, we just look at them in different ways, repeatability, looking at the same unit from one operator, reproducibility, looking at the same unit from different operators. And now we have these 3 important estimates. So, just to summarize this, we've obtained estimates for reproducibility and repeatability from the data. We've estimated that with our sample standard deviations. And so we can say that the overall equipment or gauge error is going to be the sum of the variation from the equipment itself plus any variation from the operators. And so we can estimate that also as a standard deviation by adding the variances and taking the square root. And overall, we get a gauge error, equipment error, well, let's say gauge error, reproducibility and repeatability at 0.0031 inches. Now, what we're interested in is how this measurement variation, sigma g, compares to the overall variation and our true product variation. Now, we said there was 135 observations there, and we were able to calculate the overall variation of 0.004 using all that data. So, given that the product variation, so we're going to call that sigma p, as I just wrote, the product variation contributes, as we said, the true variation plus the measurement variation is going to contribute to that overall variation. We can solve for the overall variation, we can solve for the overall product variation by using our overall variation and the gauge variation, and we come up with a value for the expected inherent variation due to the process of 0.0025 inches. Now, how can we use this information to decide whether or not we have a problem with our measurement system? So, as a rule of thumb, we will say that the ratio of sigma g to sigma p should be less than 10%. So again, the gauge variability due to the equipment itself and due to the operators using the equipment, should be less than 10% of the expected true product variation sigma p. Now, what happens in this example? Sigma g over sigma p, we get 0.0031. Don't forget, these would be, in our course, given to us. We don't have to do the calculations. We have sigma p 0.0025. Can you see the problem? Put that into your calculators. What do you get? 1.24. So 1.24 is certainly not less than 10%. This means that the instrument or the gauge error is significantly larger than our true variation, our true product variation. This is unacceptable. Very bad. But let's look a little more closely, because this is, again, an example from our author, our textbook from Professor Krish. If we looked at just the equipment error, sigma e over sigma p, we would get 0.0014 over 0.0025, which is 0.56, which is not super, but what this tells us is that at least the instrument variability is lower than the product variability, indicating that it's really our reproducibility variation that is the problem. It's causing most of the problems. And indeed, in this example, as we know, reproducibility is the error due to the different operators. And in this case, the operator C was a veteran machine operator. Operators A and B were professors who taught statistics but had no experience in using the caliper. So the instrument was used differently by the different operators. So another reason why you should make sure that your appraisers are used to using the instruments. This helps explain why, in this example, we have a high reproducibility error. And why do we still have error in the equipment itself? Well, it could be due to the fact in a caliper you have some friction due to the different sliding surfaces or unevenness in the knife edges. If you have, a strength tester, you could have effects due to temperature rises or the grip that the tester has on the specimen. There could be various practical reasons. And of course, if you have an experienced operator, that also maybe helps when they use the equipment to make sure the equipment is used properly every time. So important is to be aware of the existence of the error, and once you know that this error exists, then you try to minimize the effect of the error, either for reproducibility or repeatability. And I'm just going to write this down. If you have less than 10% sigma gauge over sigma p. Then you can say this is acceptable. Oops. Acceptable. So good. If you have the ratio between 10% and 30%, well, it may be acceptable based on the application. You need to check the cost of the measurement device. Maybe you need to make some improvements of it in it. So that's maybe a more gray area. But if this ratio is greater than 30%, greater or equal than 30%, then this is not acceptable. If you make your measurements using this system, then you're going to get values that are not useful for you. Oh, I did it again. Okay, never mind. That says acceptable. Acceptable. But if it's over than 30%, it's not acceptable, and you need to improve your measurement system before you go on. So, again, this was a few examples. We now have the contribution from Zubair Anwar from the American Society of Quality, who's going to go through an example to give you a feel for a gauge on our study with using some of the numbers.